Okay, let's take a look at the last question in topic set 5. This is actually a fairly complex question, and it's going to take a while to solve them, but let's kind of go through what the information that's given. So at the beginning it says you have an equimolar mixture of the gases SO2 and O2 along with some helium. Now, so what that means is that the number of moles of SO2 and O2 is the same, and then you have helium on top of that. And then the container is fitted with a piston. This becomes important later, as that means the volume is variable or it's not constant, right? Because the piston can move up and down depending on how much gas you have. With the initial gas mixture, you have a density at STP of 1.924 grams per liter. And the question is, if you assume ideal behavior and constant temperature and pressure, what's the mole fraction of helium in this mixture? So let's answer that first question. The number of moles of SO2 is the same as the number of moles of O2. And we can call this X for now. And then we can say that the number of moles of helium is Y. Now, so we have two different variables, X and Y. And so that means to solve for these variables, we're going to need two equations. Our piece of information is the density, but we also have another piece of information, which is STP. So let's use both of those to help us set up our equation. Let's take a look at STP first. Okay, so STP means 1 mole of any gas is 22.4 liters in volume. Now, the reason this is useful is because we also know the density, 1.924 grams in a liter. So if 1 mole gives us 22.4 liter, then 1 liter, and you get 0.04464 moles. In 1 liter, there's 1.924 grams, but it also corresponds to 0.04464 moles of the gas mixture. So the first equation we can set up is number of moles of SO2 plus number of moles of O2 plus number of moles of helium is equal to 0.04464 moles. Now we can change this to our variables, so that's just X plus Y equals to this, which means Y is equal to 0.04464 minus 2X. So that's our first equation. So the other equation we can use from the density. And the way we do that is we start with our number of moles equation, and we can convert that to mass. Now this is the number of moles in 1 liter of volume, right? We also know in 1 liter, the mass of the total mixture is 1.924 grams, because that's what the density is. Since the number of moles is made up of these three gases, what I can do is I can multiply each one of the number of moles that I have here with its molar mass, and that will give me the mass. First I take X, and then I multiply by the molar mass of SO2, 64. So I'm going to have 64X. And then oxygen, which is also number of moles equals X, oxygen's molar mass is 32 grams per mole, so it will be 32X. And then I have helium, in this case is equal to Y, is the number of moles, so then 4Y. And if I were to add all of these, I should get 1.924 grams. And I can add these two together to make 96X. I can use 4. Instead of Y, I can substitute in the term I had from my first equation, 0.04464 minus 2X. And then that would be equal to 1.924. I get 96X plus 0.17856 minus 8X equals to 1.924. And then 88.066X. This is if you were to use the molar mass, some additional significant figures, equals to 1.74544, and then your X is equal to 0.01982 moles. And remember that X represents the number of moles of SO2 and also O2. Once we find X, we can find Y. If you plug in the X value, you're going to get 0.005 mole, and that's the number of moles of helium. The mole fraction of helium would require us to take the number of moles of helium over the total number of moles of all the gases, which is just adding up all three. So 0.005 over 0.005 plus 0.01982 plus the same number again. And then that would give you 0.112 as the mole fraction. Okay, now let's take a look at the second one. Two of those gases that you have in here are going to react with each other, which is the SO2 and O2, to form a new gas, SO3. Question is, what's the density of the gas after the reaction is complete? We have SO2 reacting with O2 to form SO3. These container, the piston can go up or down depending on whether you make more gas or you make less gas. If this is a initial, which is before the reaction, after the reaction, there's two possibilities. You can either make less volume if you make less number of moles. Now, how do I know that? Because in the question, it says the condition is constant temperature and pressure. So if it's constant temperature and pressure, that means that your volume and your number of moles is going to be proportional to each other, right? It's Avogadro's law. In that condition, then you have fewer particles at the end, at the finals, compared to what you have at the initial point, then you're going to have smaller volume. Now, of course, it's also possible that you have more volume, and that comes because you have more number of moles. So the key here is then to figure out what is the change in the number of moles as you go from your initial state to the final state. And we're going to calculate it by using the reaction. SO2 plus O2 goes to SO3. We balance that out. It's going to look like that. So initially, we assume 1 liter, right? The number of moles we have are the ones that we calculate in part A. Okay, which was N SO2 is this number right here, 0.1982. And that's also the number of moles of oxygen. And then the helium was 0.005. Now you say, well, why do I care about the helium? Well, the helium, you don't care in the reaction, but you have to care about it because it's still in the container. So it's going to cause the volume to change either up or down, depending on whether the whole number becomes bigger or smaller. Now the reaction is between the SO2 and the oxygen. So the first thing to figure out is what's going to be left over at the end. Well, if we take the number of moles and divide by the coefficient, the one for SO2 is going to be smaller, which means that there's going to be some O2 left over and some SO3 made. So this is initial. In the final state, then, we have helium going to stay the same. We have some oxygen left over, and we're going to have some SO3 that we just made from that reaction. So to get the number of oxygen left over, we have to calculate the number of oxygen used, and that's fairly easy. We take the number of moles of the SO2, because that's our limiting reactant, and then we just multiply by the molar ratio, or the stoichiometric ratio, which is 1 to 2. So that's half of this number that's used up. Since that much is used, then the number of moles of oxygen left over is just whatever we started with minus what we use, which is this number. Okay, so this is O2. And then we have to calculate the SO3 that's made, 0.1982 moles of SO2 times 2 to 2 ratio. So 0.01982 moles SO3. Okay, so if I add up all the total final number of moles, gives me 0.03473 moles. Okay, this is my final number of moles. My initial number of moles ends up being 0.04464. P and T are constant, so V is proportional to number of moles. We started with a number of moles that's 0.04, and we end with a number of moles that's 0.03. So we've dropped in number of moles. So that means that the volume will also drop. So this piston is going to drop down. And so the question is, how do you calculate that volume final? Remember, we can use that Avogadro's relationship. V1 N1 is V2 N2. V2 is just V1 times N2 over N1. Our V1, remember, was 1 liter. Our N2 is this number that we just calculated. Our N1 was the 0.04464. And if you calculate all that, you get 0.778 liter. Now, that's the new volume. What about density? Because that's what they're asking us. Well, density is mass over volume. When the reaction happens, remember that we have conservation of mass, so whatever this two things there consume, they basically makes that. And the mass of this new guy would be equal to whatever you lose from here and here. And then you add that up to the leftover O2, you basically get the same mass back, the same mass of SO2 plus O2 that you have originally. And then you add back the helium, you get the same mass that you have from the very beginning, which is 1.924 grams. Since we have conservation of mass, total mass in the flask, because we're not letting things go in or come out, is Still 1.924 grams. But the volume has changed. It's gone from 1 liter to this number right now. So then the new density will be the old mass, but then divided by the smaller volume. And that would give you 2.473 grams per liter. All right, so that's a pretty difficult problem in gases. And so just make sure you understand sort of all the different steps I did here to solve that problem.